first, before we talk about stats, go into, sorry, I have to click a dialog box. There we go. Go into not only why is empiricism valid, but why can you not use what we think of as, logic? Why we can't just logic our way out of a problem, and why empiricism is actually better than doing that. So once we set that up, then we can actually look at some examples of different types of statistics, and then we're going to end with some data that I've analyzed. I pulled from the FBI's Uniform Crime Reporting. So we're going to take a look at crime data in Arizona, California, Nebraska, and North Dakota, which seemed like they were pulled completely out of a hat, but I'll tell you why I used those in a second. And then we'll look at some work that I'm doing. I'm using stats in to possibly try to solve a crime. So you're going to get kind of like an episode of that TV show Numbers at the end of this talk. So who am I? Like, why should you listen to me about any of this? Well, in addition to knowing Martina for a long time, I've taught research design and statistics for 6 years, originally in the psychology department at ASU while I was a grad student. Then I was an adjunct faculty there. Now I teach in the College of Health Solutions, but in addition to teaching classes about speech and hearing and health, I also teach what they call biostatistics, but it's the same thing, you just use biological and health examples. I'm also a researcher and statistician with the Samba think tank at ASU. Samba stands for the Science of Art, Music, and Brain Activity. And I put this on our webpage. Is anyone from Samba here, or are you guys all Leeds members? I'll let you tell me in the chat, which I'll also open. So if you have any questions throughout, you can just ask in the chat. I've got it on my second monitor here. So I also, in addition to teaching stats, founded Yggdrasil Data Science in 2017, which is a statistics and research design consulting company. I've worked with aerospace firms looking at the design of their wings, which ones will last, statistically longer. I've looked at law enforcement officer training programs. It's actually law enforcement and military virtual reality training programs. It's super cool. I'm totally bummed I'm not working with them anymore, but I don't have time. And I also worked briefly with MUFON, which stands for the Mutual UFO Network, which I know seems kind of ridiculous. One of the things they wanted me to do, of course, was like, can you tell us if UFOs are real? And I'm like, no, I cannot tell you that, because I don't know. There's no way that data science will be able to tell us this. But there are two things that I'm really proud of that I was able to do. One is I was able to take a look at some different UFO reporting flaps, and just based on the distribution of when they came in, we could kind of tell if one was definitely a hoax versus maybe people were mistaken about seeing the Starlink, Elon Musk Starlink satellites or something like that. So of course we don't know what they saw, but it looked like statistically the patterns of the reporting were coming in as maybe it was actually something they were seeing versus some that were definite hoaxes. And the other thing I was able to do was prove a racial bias in what MUFON accepted as that was a UFO, right? So they have these listings of things that they think are not and things that they think are. And I was able to show them that their decision criterion is skewed based on what the demographic makeup is in the places where these are coming from. So I like that a lot, because it doesn't matter what you think. If you think UFOs are complete BS, which I'm sure a lot of you do, and that's fine, like I have no idea. And then there's some people that are hardline believers, shouldn't be a racial bias no matter what. So I'm really proud of that work. I also developed a couple analysis procedures. One is called ROTCore, which uses something called multidimensional analysis to turn into a statistical tool. And then the second thing that I just did was I came up with a new contact tracing procedure that you don't have to give up your data. So a lot of people are worried about giving up their privacy. With this new contact tracing procedure I devised, you don't have to give up any data. As soon as the algorithm can compare where you've been to another one, that data is deleted. It turns it into a series of zeros and ones. Nothing is stored. No one will be able to know where you were. And so that is something I'm publishing right now. Also, Nicholas, no, MoveFund did not like giving had a racial bias, and that is why I don't contract with them anymore. They didn't hire me again after that. But I thought it was worthwhile to know that. It was actually their director of science that they had hired who brought me on and wanted me to look at that. And then as soon as I found that that was true, he brought it to their attention. He got fired and they stopped hiring me to run data science for them. So unfortunately, instead of going the right way about things and changing their organizational structure, they just doubled down on yeah, totally scandalous, right? Okay, so let's talk about experience versus inquiry. So experience is flawed. I mean, it seems like we can logic our way into things or out of things, but really we can't. We need to use empiricism. So one of these that I like to talk about is the 79 is faster than the I-10. So if I'm traveling down to Tucson to visit you guys, if I was going to come down and give my talk in person, I would definitely take the 79 from Queen Creek, which is where I am, down through Oro Valley. I think it's faster than the I-10. And it seems like it is, but like I can't be in two places at once, right? I have no idea what the I-10 is like at the same time that I'm on the 79. I know that it was really slow one day when I took the I-10, but I don't know what the 79 was like that day. So there's no comparison group. I'd have to have another person leaving at the same time from the same place, traveling at the same speed, and then see who got there faster. And also, the day it took me 1 hour to get down there really stands out in my memory, which taps into something called the availability heuristic. So 1 hour in the car, boom, I'm in Tucson. I was probably driving way too fast, but it was amazing. And that's the same reason I don't like flying, this availability heuristic, because there are points of data about flying that stand out to me, and these are like plane crashes and horrible things. I don't see all of the times that planes land safely because there are no news reports about today 18 planes landed safely. No, that's not true. What you hear is today there was a plane and there was smoke all over in it and it landed safely, but it might not have. And so then what's in my mind is flying is unsafe, even though it's totally safe. It's not environmentally conscious, but whatever. And then the last thing about taking the 79 is it takes me past Beyond Bread. So I have a little bit of confirmation bias there. I can stop in and get a pretzel. I have a reason to want the 79 to be faster because if I take the I-10, the only thing I pass is the donut wheel, which is still good, but it's not as good as Beyond Bread. So these are all reasons why, even though I think I know what I'm talking about, my experience isn't the same as actually testing it out. So what I want you to do is look at the screen. I'm going to flash a picture up really quickly, and then I'm going to ask you a question. Okay, ready? Okay. Those were M&Ms. Somebody tell me what do you think, what color was most prevalent in that grouping of M&Ms? Blue, red, red. Okay, cool. Well, damn it, Martina. It was blue. Red is a great answer. Sometimes I get yellow, which is really like I dance around when I get yellow from this from this example. Blue is definitely the most represented color, right? And yellow is not. Red, even if you accidentally saw the orange as red, which I think when you flash it that quickly you might, there's still 5, 6, 7, 8. There's still more blue than there are red and orange combined. So it's a perfect answer. I mean, you guys are wrong, but in a way, you're totally right to show what I want to talk about, which is, again, this availability heuristic. So these more obvious pieces of data are just more obvious. We had a blue background, the blue doesn't pop as much, and so you see the red and the orange is sticking out. It doesn't necessarily mean that these ones that you see more are more representative of what's actually going on. The only way to really do it is to sit there, count all of these, and then find out, what's most representative in that picture. You see this in the news, right? I mean, the loudest, most flamboyant critics of things get the most airtime in the media. It doesn't mean that most people believe what these people are saying. Like, these are like the extremes. A lot of people tend to be in the middle, but nobody hears the person that says, I like to be rational and think about these things. It's boring. They never get on the news. And in terms of things that you guys might be dealing with, the sleepwalking defense. I'm sure you guys know about this guy that killed his wife, and then he said he was sleepwalking, and I believe he ended up getting off with no punishment. I mean, you Martina, you can correct me if I'm wrong, but I think it worked, or at least it almost did. There was a lot of airtime about that.
Or something. I know which case you're talking about.
Yeah. What was the first part of what you said?
I think he got a lesser sentence. I don't think it 100% worked.
Okay, yeah. Then that makes total sense. I mean, still less than you would assume of stabbing somebody 40 times. And then also insanity defenses, we hear about these a lot, and they don't typically fly. I don't know about that from the legal side. I mostly know about it from the psych side of using insanity defenses, that it's not advised. But certainly we hear about these, and these are not the common thing. And I'm sure before you guys got into law school, this is what you thought of, and then you get into law school, you see the nitty gritty. And of course, these aren't representative of what you're actually doing. They're just outliers, but the outliers are more available to your mind. So really quickly, we'll talk about bloodletting, because I like this picture of this person with absolutely no neck and gigantic arms that's shooting blood into cups here. It's the most effective treatment for plague, at least in 200 AD. And we have Galen of Pergamum to thank for that. He's the first person that wrote about bloodletting. And this was actually, I mean, you think that bloodletting is from ancient times, but it was actually pretty widely used up until the 1700s. These people are pretty modern. This is like Hamilton is set slightly after they stopped bloodletting. So kind of ridiculous. So let's take a look at this. We see people who let blood, 20 of them lived, but people who kept their blood inside of them, only 10 of them lived. So it looks like the bloodletting is working. That's because we don't have the full picture. And this is why empirical inquiry is key. We have to also look at who died. So of the people who engaged in bloodletting, 80 of them died versus 40 who kept their blood inside of them. And then you can look at the total, it's 150. It's the same percentage who lived and died. Bloodletting does nothing. And this actually seems true. They weren't taking enough blood to harm the people who, were sick, but it certainly isn't getting rid of whatever is affecting you. So there's no evidence for it working. And the reason why it was so pervasive in culture was because no one actually looked at it empirically until around the 1700s. Until then, we're kind of going based on what we see, the availability heuristic. Look at all these people who lived and who engaged in bloodletting. That's just because it's more popular. One other thing I want to talk about, this brings up central tendency. So now here's where we're going to start talking about stats. These numbers are idealized, but of course, real values are not uniform. We would not expect any real value that you get to be uniform. Think about height. If you measured the height of everybody in this meeting, an average, but we've also got some tapering around that. And this is, of the the bell curve, the normal distribution, the Gaussian curve. This is where that comes from. There's an average, and it's you know, pretty present. Like there's a lot of people that are that average height, but there's also an expected variation around that average as well. This is where Al-Kindi comes in. So here's the music part of the talk. So Al-Kindi is a musician and a philosopher and a cosmologist and a mathematician, like a total Renaissance man, but he predates the Renaissance by about 800 years. The way that he brought central tendency into the forefront was by estimating the number of bricks used to construct possibly this exact fort right here. So what he did was, somebody challenged him of like, how can we figure out how many bricks were used in this fort without counting all of the bricks? And he thought, well, what we can do is we can look at different sections, figure out how many bricks were used in those sections, and then apply that knowledge to the whole thing. So he pulled, they didn't use feet, but let's just use some anachronisms here. So they looked at a 2 foot by 2 foot section and counted the number of bricks there. A couple different 2 foot by 2 foot sections, because these bricks aren't uniform. There's some variation, right? So we can look at the central tendency of how large these bricks are, but we don't know the exact, they don't have an exact measurement like we would with bricks today. So he estimates this is the average number of bricks in a 2 foot by 2 foot section. We can apply that knowledge to this fort, and he comes up with a number. Then he sends these, like, you know, little underlings out to actually count the fort, and he's right within just a couple bricks. And so then they're like, wow, that's so crazy. And he's like, I'm going to go write a song about it. Why don't you ladies come with me and sit on this cool rug? And that's what's going on in this background picture here. So here's a little bit of work that I I don't know the song. I'll try to come up with it, and then at the end, if I have extra time, I'll try to recreate the Al-Kindi song. So here's some work that I've done with bird songs and human songs. We're looking at change to the next note. Thank you, Kaylee. So human songs, if you think about it, typically the next note that a song is going to play is the same note. So there's, of course, variation in the notes, but a lot of things are like da-na-na-na-na, like they're playing the same note in a row. And so you get a distribution around that, but what you see is basically we've got central tendency, which is 0, and then from there we can change 1 semitone, 2 semitones, and more, and you gradually decrease as you get further and further away. If you look at birds, they do, weirdly, exactly the same thing. So birds tend to make the same sound, the same pitch of sound right after that pitch, and they'll go out from there, but it has the same ever decreasing slope to it that human songs do. But what I want you to notice is the variation is different. So bird songs, the average is 0, but the variation is much wider. So the distance between these two lightsabery looking bars is a little bit wider than in the bird songs than it is for the human songs. So in addition to a central tendency, we also have these measures of change, of variation. A lot of times we call this standard deviation. You might see it as variance, but that's just how much slop there is around that central number. And one other point I was going to make about the central number, usually we use the arithmetic mean or the average. Occasionally you can use the median, and there's, I'm not going to go into it because it's kind of an advanced stats topic, but there are reasons why you might use the median instead of the average. It has to do with if your data aren't normally distributed, then you should use the median. But again, that's not something that we're going to talk about. You can still get a variance and standard deviation around either one of those. Okay, so now that we know about the things that we are using, our average and our standard deviation, our variance measures, we can talk about the main questions that we deal with in stats. And really there's two questions. One is there a difference between two things, or is there a relationship between two things? And I'm saying two, I just realized that's actually not totally true. It can be, is there a difference between 2 plus things, or is there a relationship between 2 plus things? So we can look at a difference between groups if we're looking at a difference. Just men and women, do they differ on some quantity? People in prison versus people out of prison, do they differ on some measure that we've taken? We can also look at a difference because of change. So we can actually manipulate something and then measure because of the change. So we can give someone, you guys all took the LSAT. There's multiple methods of studying for the LSAT, just like there are for the GRE. So we can have somebody engage in one of these studying practices versus another, and we know what we've done there. And then we can compare their LSAT scores. So we can look at differences because of a change that we've actually made. If you want to know the nitty gritty, the terms that we actually use, this is a pseudo experiment because we're not actually manipulating anything. We're just looking at differences between groups. There are some, things going on there where you can say, yes, there's a difference between, say, men and women, but there could be, it doesn't mean the difference is due to biology. It could be social. It could be whatever. When we actually have something that we are changing directly, like the method of studying for the LSAT, this is due to what you're changing, because these people should be equal in every respect. And you can test that. You can see if there's a difference before you give them the method of studying and then after. And you can know that what you've done is where the difference is. Now, with the kind of data that you're going to be dealing with, I would assume that a lot of times it's going to be one of these pseudo experimental type variables. You can look at cases that have already gone through, and you can look at outcomes. And it doesn't make it any less valid. There's a lot of stuff that you just can't assign. Smoking, you cannot assign someone from birth to be a smoker, but you can look at differences between smokers and non-smokers. It requires a little bit more evidence than this one, but that's okay. Now, if we're talking about a relationship, we can look at, do two quantities change together? That would be a correlation. Or we can look at, can we predict a quantity from other quantities? And that's where it gets really interesting. So these are correlation right here. Do two quantities change together? And regression right here. We can see if we can predict one quantity from others. This is the kind of graph that you'd see if you're looking for a difference. So you get a bar and you can just see, oh, one is much taller than the other. There is a difference. Versus when you're looking at a relationship, you get a line, a lot of points in a line, and you can see if the line goes up, there's a relationship. And if it's flat, there's no relationship. One of the things that I think is really great to look at with, one of the examples that I was presented with when I was learning stats about regression was pay. So the data set that we had was actually taken from a Fortune 500 company, because there were female workers at the company who were alleging that they were being paid less on the basis purely of being female. So a lot of data was put into this regression equation, how long they'd been there, so seniority, their most recent 3 years of evaluations, their gender, some other things. And what came out was the biggest predictor of their wage was seniority and then what their gender is. So the longer you've been there, the more you get paid. There's an interaction with if you're female. So they actually proved that statistically these women were getting paid less. And I do think that ended up going to court and being the major piece of evidence to try to equal out these pay structures. Okay, so let's talk about differences first. Now here we're going to bring in the beer aspect. That's not a typo, that's just a really stupid pun. There's barley a difference. Also, it sounds Irish. So Guinness, back in the 1800s, has 2 strains of barley that they are thinking about using to make their beer, Guinness Draft. And this guy, their head brewer, oh man, of course, his name is slipping my mind. Oh, good thing it's on my slides. William Seeley Gossett right here decided that he would take it upon himself to create the t-test to find out if there was a statistically significant difference of yield between two barley types. So there's an average, of course, and that average is different from year to year, plant to plant, but looking at various plants through, I think, a 5-year period, he was able to use statistics to show that the darker barley up here, this isn't an accurate picture of what it was, but it was a slightly darker barley that they were using, actually produced more yield. So by planting the darker barley, they would be able to produce more beer in the same amount of time, which of course, if you're a brewer, that's fantastic. So he's a chemist, he's a brewer, he's a statistician. He's such a statistician and a beer lover that he developed the actual test to see if there's a difference between these two barley outputs. Now that's another key aspect to thinking about why statistical inquiry is worthy. And that's because if you go into business law, you can actually look at what does your company consider successful? When are two things different from each other? If you're looking at patent law, does something produce significantly more than another? So seed patents would be one of these, like a direct analog to what we're talking about here. Somebody might allege that this seed was developed from their copywritten genetic code, but if you can show that it produces a statistically significantly different yield, then it's not the same seed. There's something that is statistically different about it. So that's another reason why you might want to keep that in mind. So very quickly, just to go through some of the actual math and graph portion of what you're looking at, in case you read studies through the rest of your time in Leeds or your time in law school or as a lawyer, what are you looking for when you see a t-test? So a t-test is going to return a t-statistic, and larger is better, essentially, right? So a bigger t-statistic is better. Right here up in the top, the blue is further away from the green. This would be the average yield from the darker barley, and the green is the average yield from the lighter barley. There's a large difference. There's a big t-stat. So bigger difference, bigger t-stat. It can give you an idea of how much difference exists, but really, you don't need to know any of these t-stats by heart. You just need to know that bigger is better. And there's jokes I could make about that, but there's a different joke similar that I'll make later in the slides, so we'll save it. From this, though, we get a p-value, which stands for probability value. And this is antithetical to what you might think. A smaller p-value is actually better. So the larger your t-stat, the smaller your p-value is going to be. Why is that? Because what the p-value is telling you is, what is the chance, what is the probability that these two sets of numbers came from the same group? So what is the chance that we've got the same kind of barley, and we've accidentally taken all of this high yield from that group and all of this low yield from the same group? If it's a low probability, then you get a low p-value because you've got a large t-stat. So really the probability value, if you take one thing away from this slide, is it's the chance that things are coming from the same distribution, the same group. And if there's an unlikely chance that things are coming from the same group, then you get a smaller p-value, a larger difference, and that's why smaller p-values are better. We're always looking for less than 0.05 is the basic. So let's kind of look at that. Thanks, Martina. Let's kind of look at that really quickly. We've got a group of Dutch and Indonesian lawyers. This is from real data. The average height of a Dutch male is 6 feet. It's 5'7" for females. And the average Indonesian height for males is 5'2", and 4'11" for females. So these are the tallest country in the world, shortest country in the world is Holland and Indonesia. And so the Dutch firm is paying for dry cleaning, right? And these guys are at the same hotel, and a group of suits that are charged to the Dutch firm account averages a height of about 5'4". So what is the chance that we just accidentally got a bunch of really short Dutch lawyers? Does that seem likely, or is it more likely that the Indonesians heard that the Dutch lawyers were getting their dry cleaning for free, so they just said, yes, we're from the Dutch law firm? It's very likely that this size fits the height of these Indonesian lawyers, and it's very unlikely that it fits the size of the Dutch lawyers. So we would expect a small p-value. And our benchmark is roughly 0.05. I mean, less than 0.05 is considered significant, but you'll see studies that get to 0.06, and that's okay. You know, there's no magic that happens at 0.05. Smaller is better. But that's not always true. Here's that other joke I was talking about. It's not the size of the p-value always. It's the effect that it has. So we measure all of our tests with p-values. We can look at correlations with a p-value. So a more significant correlation has a p-value stated with it. If you're not seeing the connection between difference in two groups and how something can be correlated and have a p-value, it's actually looking at the chance that that correlation comes out of two quantities that aren't correlated at all. And so if it's unlikely that those two quantities that are highly correlated come from a group that is not, then you have a high p-value. So everything essentially comes out of these Gaussian normal distributed curves. Everything's measured with a p-value. But studies with a larger number of data points are going to be more sensitive to changes. So you're going to get an accidentally smaller p-value just because you have more subjects that you're testing. That doesn't mean that it's actually more significant. That just means that it's overpowered. So another thing that you need to look for in studies that you're evaluating as a lawyer, as an empiricist, is the effect size. Effect size gives an unbiased estimate. So you can have two studies with different population sizes, which are going to have two different p-values, but they might have the same effect size. And so don't let somebody fool you by saying, look, it's a tiny difference, but it's a significant difference. No, it's not. You just have a million participants. The effect size shows that there's no change in these groups. So you have to look at effect size. Good papers will always put the effect size into scope for you. They'll put it into a reference frame. So they'll tell you an effect size of 0.2 is small according to these standards, or it's large according to these standards. So that should be in the paper. But if you want to familiarize yourself with different kinds of effect sizes, that's also good. So let's quickly take a look at relationships. So correlation is the basic relationship. These are obviously going to go from -1 to 1, but the distance from 0 is how large the correlation actually is. The sign is just saying if they change together upwards, negative is going to say if one moves up and the other moves down. So it's a negative correlation of 0.7 is just as big as a positive correlation of 0.7. It just means that they're changing in opposite ways. There's a lot of relationships that don't correlate, and you can see some of these here. So a circle, there's definitely a relationship there, but it wouldn't give you a good correlation value. It would give you a 0 correlation value. Okay, so there's a study in 2011 that found a significant correlation between dark chocolate consumption and Nobel Prizes awarded. So more chocolate equals more Nobel Prizes. And from this, they decided that it was actually dark chocolate that is enhancing mental functioning. This is complete BS. There's no reason that we should believe this. I don't even know how it got published. This is totally wrong. Correlation is a super useful tool. You can predict one value from another. So you might be able to say this country eats a lot of dark chocolate. They probably have some people that might be getting Nobel Prizes. That doesn't mean that it causes it. If you take any statistics class, they'll drill into your head, correlation is not causation. You should totally learn that. There's probably a moderating variable. And in this case, it's GDP of a country. The higher the GDP of a country, the more dark chocolate the citizens are gonna eat. And also, the more the scientists in that country are gonna win Nobel Prizes. It doesn't even mean, if you look at some of the people that have won in Switzerland and the United States, they're not all Swiss or American. A lot of them are from other countries. They've come to these universities and they're winning Nobel Prizes from Switzerland and the United States, but they're actually from a different country. So it has nothing to do with dark chocolate. Don't eat dark chocolate because you think it's going to make you smarter. And certainly don't eat baking chocolate for any reason. It's disgusting. Yeah, reviewer 2 dropped the ball for sure. I don't know how. And that's in like an okay journal too. I don't know how that got in there. It was ridiculous. Okay, so again, is there a difference? Is there a relationship? This is what you're looking at. This is what stats can answer for you. There's a couple other things that you can look at with statistics, but really it comes down to these 2 questions. That's all that you're going to see. So let's take a look at this uniform crime reports that I've got from 1960 to 2014. So first, I wanted to look at violent crime in Arizona and California. Is there a difference between Arizona and California in violent crime? So I did this as per capita because, of course, California has more violent crimes if you just look at the number. Sure they do. It's a huger state, right? It's roughly twice the size of Arizona, I think. So if we cut this down to per capita, is there still a difference? Well, the Arizona average is 0.0048 crimes per person, which should make you feel somewhat safe, I guess. With a standard deviation of 0.0015, you can see that California is a bit higher, but their standard deviation is also wider. Is there a difference? Well, our T is 108. That's pretty huge. You're definitely going to see a difference here. Our T is actually, sorry, I'm talking completely out of my ass. I'm sorry. Our T is 3.79. It's a decent size. And the p-value is great. It's lower than 0.05. It's significant. But we have a lot of data here, right? We've got 45 years of data that we're actually looking at. No, 55 years of data that we're actually looking at. So what does our effect size tell us? The Cohen's d effect size is roughly 0.75. And I've got the benchmarks for Cohen's d right here. 0.2 and up is small. 0.5 and up is medium, and 0.8 and up is large. So it's verging on a large effect. It's still in the medium range. You might call it a medium to large effect if you were publishing this, because it's right near that cusp. So it's a decently sized effect. It looks like California does have statistically significantly more crime, violent crime, than Arizona does. If you look at property crime, you're not going to feel great about living in Arizona, but that's why I'm not showing you. There is more violent crime in California. Don't look at property crime unless you hate yourself. Okay, so now we are going to look at property crime, but we're going to look at it as a function of between states. We're also looking at a significant difference between property crime and violent crime. So this is where we've got multiple differences. Is there a difference between the type of crime, property versus violent? Is there a difference from state to state? And on top of that, when you start looking at multiple things, is there an interaction between the two? So does the difference between the two different crimes change as you move from state to state? So what you can kind of tell from this graph is, first of all, property crime per capita in Arizona is out of this world. We definitely have maybe a problem with property crime. But it's okay, because I'm not getting murdered. My stuff's just getting taken. So I guess I'm more okay with that. There is a significant effect of state. So you can see the p-value there. I should highlight this for you, is less than 0.001. This is another type of effect size. It's called eta squared, and it's 0.12. To put that into scope, a frame of reference for you. 0.12 is a medium effect. So there's a medium effect, but there's a difference from state to state. And you can see that, you know, visually. These bars at the top, these are called error bars, and these represent 2 standard deviations of change. So if the 2 standard deviations don't overlap at all, that's a huge difference. If they overlap a little, you can expect more of a moderate effect, or none, depending on how much they overlap. There's also a significant effect of crime. I'm sure you can see that. 0.66 is a very large effect, but that's visually apparent in this graph. And then there's also a significant interaction. It's a small interaction, which again, you can kind of see. Overall, as property crime decreases, violent crime decreases. This is true for North Dakota and Nebraska, but Arizona and California make it a little funky because they're kind of flipping. Arizona more property crime, but less violent crime, and California is more violent crime, but less property crime. So it's a small effect. There's something there, but kind of small. I didn't look at zip code by zip code, Martina, but I wonder if there are some areas that are pushing that. Yeah, I think that like right outside of proper Flagstaff, there's a lot of property crime too. It's all the, well, this is not PC, but it's all the meth, you know? So now let's take a look at correlations. Are 2 things related? So do property crime and violent crime move together? Well, you should know from here, overall, they do. And that's what we find in this case too. So here we're actually directly inquiring about what is the relationship between property crime and violent crime. All of these little star points that you see, these are the actual numbers that I'm pulling. So this dot is a year where you can see that there was violent crime was right here at 0.004 and property crime was at roughly 0.03, something like that. So all of these represent a certain point in time. And from there, we derive this line, this best fit line that cuts right down through the middle. And this is a significant correlation. It's 0.8. So remember that these range from 0 to 1, either +1 or -1. So this is a pretty large correlation. And now I want to know if we can predict murder rates from other kinds of violent crime. So we have 3 possible predictors that they give us from the FBI. We've got aggravated assault, rape, and robbery. Now, one thing I want to say is recently the definition of rape has changed. This is what I'm looking at here is called legacy rape, which is not quite as encompassing as what rape is considered now. In this case, it's only women and it's only certain types of assault that get called rape. Now, the new definition of rape can involve men, and then there's an expanded definition of things that are accounted for there as well. But anyway, these are the 3 things we're looking at. And what I'm using is called a stepwise regression. If you're doing a regression, I think you should always use stepwise. It's the best. It's the best in my opinion, and other statisticians as well. Not all of us, but most of us. What it does is it takes the single most significant predictor of all of the predictors you put in and puts it into the model. And then it reevaluates the model and sees if any of the leftovers would change the significance of that model again. So that's why I like the stepwise regression. You're not getting anything in the model that isn't significant, and the model may change once you put things in item by item. So here's what you see in Arizona. Robbery and aggravated assault predict 96% of the variance in murder. In California, robbery and rape predict 97% of the variance in murder. In North Dakota, aggravated assault predicts 50% of the variance in murder. In Nebraska, robbery predicts 46% of the variance in murder. So if you look at all these, what is the common denominator? Robbery, right? So that's telling us that robbery highly predicts the rate of murder. The rates of robberies highly predict the rates of murder. Aggravated assault comes in twice, rape comes in once, and then Nebraska had only robbery. The other thing I should point out is that you do get a percentage of variance for all of these, and I'll tell you, Robbery and aggravated assault together make up 96%, but robbery alone in Arizona was 91% of the variance in murder, and in California it was 93. So the other significantly changes the predictor, but really robbery is the one that takes the cake. So that's what you can learn from this. Of course, there's some outliers. North Dakota is kind of strange, but you can expect that. Natural variation. Variation is always messing with your data. Okay, in the very last few minutes, I want to talk about my own, this is the episode of numbers that you were promised at the beginning. So if you remember a few years ago, we had 2 serial shooters active at the same time in Phoenix. One was arrested, and there was an arrest made in the other case, but that person was released. Can statistics help us identify the second shooter? I think it can. Let's see. So in August of 2015, the freeway shootings began. Most of these occurred on I-10 and right within Phoenix proper, not within the metro area, not out like where I live. Like technically it's Phoenix, but it's not. This was all within actual Phoenix, between 83rd Avenue and 36th Street. If you have not been to Phoenix, you're not missing much. But also, the grid is set up kind of like a number line. Avenues are negative numbers, and streets are positive numbers. So this is kind of where I got the idea. It was like, oh man, it's just like a number line when I see on the news the map of where these shootings are taking place. So one thing I know is that animal foragers, this is from some work I've done. This is not from my publication, but I've done work in this area. Animal foragers will move from their dens, their homes, their base, out in random directions for random distances. If you average the directions and distances together, it usually puts you right back on top of their home base. And you can see that the point of the arrow in all of these cases, we're looking at ants here, is putting you mostly back right on top of the anthill. So here, there's no significant difference from the top of the anthill. Here, there's no significant difference from the top of the anthill. Here, there is a slight significant difference. Notice that it's less than 0.05, but we have other benchmarks too, less than 0.01 and less than 0.001. So this is just a slight significant difference, but you can see how close it actually is to the anthill, which is right at the cross of those crosshairs. So what if human hunters worked like this as well? Could we use statistics in the same way to find where the shooter's home base was? That's what I did. Also, I want to really quickly point this out to you. The Phoenix PD seized guns from something called Mo Money Pawn in this investigation. That's going to come up again. Okay, also, so is August 2015. So here's the Freeway Shooters activity area. What you're seeing here is 1 standard deviation from the midpoint out. So this is where I think the freeway shooter may have lived, is somewhere within this area. This is a large area, of course. I mean, it's covering quite a few square miles of real estate. These little markers that you're seeing here are the arithmetic averages, the right in the center of these different places. Why there are 2 is because most of the shootings happened along this freeway. So I'm predicting that this person would live somewhere near this exit right here. But one other shooting occurred way up here. And if you factor in the north-south angle of that shooting, then you get this large area right here as well. So it's possible that they could be in this area as well. Let's move on to the second shooter. So the second shooter was first identified in March 2016. This is him. He drove a bus for Valley Metro. Oh yeah, no problem, Madeline. Thank you for stopping by. He was a lot deadlier than the highway shooter, the freeway shooter, I should say. Eventually, we know that his name is Aaron Saucedo, and he does live within 1 standard deviation of the activity area of his own crimes. He also frequently visited his father's house, which is also within the 1 standard deviation activity area of his crimes. And you can see that the midpoint between the residences is almost the arithmetic center of the crimes that he committed as well. The first killing that this guy committed was his mother's boyfriend. So the mother and the father aren't together. The first person he killed is the mother's boyfriend. When did he make that first killing? It wasn't in March of 2016. This is when he was first identified. It was in August 2015, the same time that the freeway shooter became active. 11 days before the first freeway shooting, in fact. Now take a look at this area here. This is where Aaron Saucedo lives with his mother. This is where Aaron Saucedo's father lives, down here on the I-10. This is the midpoint of this activity area, and this is the midpoint between Aaron Saucedo and his father's house. Very close together. So this evidence alone makes me think that this is a valid statistical tool that we can use to at least have an idea of where criminals could be. Of course, this doesn't take out traditional detective work at all. It's just another small piece of the puzzle that might be useful. But let's go further into tinfoil hat territory. So was there only one shooter? The gun that was used in the first Saucedo killing was obtained by Phoenix Police Department in the Mo Money Pond seizure. However, they didn't know it was used in a murder at this point. They got it, and they actually looked at a different person's gun, Leslie Merritt Jr.'s gun, in fact. His attorney, when they were getting him off for being the freeway shooter, noticed that in some of the evidence the Phoenix PD collected, there was a car matching Aaron Saucedo's BMW in traffic cam footage. That traffic cam footage was later used to arrest Merritt, but this BMW was in that same footage. So what they did was they got a screen grab of the traffic cam footage from when one of the shootings was made. Also, there's a partial license plate match between the BMW in the traffic cam footage and Aaron Saucedo's BMW. So it's not just the same make and model of car. There's I think 4 of 6 characters match the license plate. And what happens when we overlay the two activity areas? They're very similar. So red is the freeway shooter, blue is the Maryvale street shooter, the one that we know as Aaron Saucedo. Look how closely their arithmetic centers align. Now what happens when we consider that they're part of the same data set? So number one thing that happens is our variance shrinks because we have more data points and our average gets a little more peaked. And now you can see that still Aaron Saucedo's residence is within the activity area, so is his father. And again, he frequently traveled to his father's house and stayed overnight often. So this area was, you would assume home to him, anywhere between his house and his father's house. And now look at the midpoint between the two residences and the midpoint of this activity area when you consider that all the shootings were made by the same person. Almost right on top of each other. In fact, I think it's a 1.7 mile difference between the two. So we know that animal hunters and foragers effectively use these techniques. This activity area fits Aaron Saucedo. And one thing that happened, which is really interesting, was Leslie Merritt's gun, which was seized from Mo Money Pond. Phoenix PD said that his gun, Merritt's gun, matched ballistics evidence from one of the freeway shooters. But later in the trial, the evidence evaporated. They said that that evidence had never existed. Is it possible? Because we know that Saucedo's gun that was used in the first killing was picked up in that same Mo Money Pond seizure. Is it possible they switched the ballistics match? Did they actually have the freeway shooter before he killed 9 people and they pinned it on the wrong guy? It's possible. I don't know. Maybe. But at least the statistical evidence looks like it may have been a single shooter. They overlap really well. And if I go back here, this point way up in the very upper left-hand corner, this is where Leslie Merritt Jr. lives, way outside of 1 standard deviation away from the arithmetic mean of these shooters. So I don't think he did it. Of course, the state doesn't agree that he did it anymore either. He was let off. but some investigators still think that he's the guy. That's the end. Thank you very much. I will stick around for any questions if they go beyond the 2 minutes that we have left. You're welcome.
Whoever that was, go ahead. I was going to ask, do you?
Yeah, you're welcome.
What, so that seems like something that could be brought in by an expert witness, not necessarily an attorney. But
yeah, right.
Like
exactly.
How might a court raise something like that? Because in a way, it's kind of all theory, right? It's not, you know, hard evidence.
I don't think they should weigh it very highly at all. Sorry, go ahead. Go ahead.
Oh, I think we have a lag. That's okay. Go ahead, Jake.
Oh, okay. I was just saying, I don't think they should weigh it very heavily. I think that it is evidence that Leslie Merritt Jr. might not have done it. Of course, there's other evidence that shows that he might not have done it. I think this is just one small piece that can put that puzzle together. I don't think it should absolutely not be used to convict anybody. It's not, the area is too wide to say that anyone has actually done this. What I think it should be used for is before you get to the conviction phase, like while you're still searching for someone who's doing these crimes, serial shooters, serial rapists, serial killers, anything like that, it can help you narrow down the area. Certainly better than what we think of as criminal profiling, which is just mostly bullshit on a plate. There's not a lot of evidence for profiling. It's based on mostly stereotypes and the crimes that we've solved, and there's not a lot of actual evidence there. It's mostly just kind of social psychology hand waving. This, I think, is actually based in real, actual statistical inquiry and should be used instead of profiling. In terms of convicting somebody, I do not think anyone should go to jail with this being the only evidence that is not nearly strong enough for that. Piece of a multi-layered puzzle, maybe, but definitely not the only thing. Now, the other studies that I've showed you, things where we're not just looking at someone's activity area, those are more solid. So this is more exploratory, what I've just shown you, but when you can actually look at two quantities and say that people who are not taking medication A are significantly more likely to live longer than people who do take medication A, then that should be used in court for sure.
So, Dr. Patton, have you ever been like an expert witness for statistical issues?
No.
Okay.
I would like to, but I haven't. I mean, I'd love to see the other side of it to be able to tell you guys what to expect. Like if you were going to get one, what kind of questions to ask, what kind of questions the other side is going to ask of the expert witness. I haven't, but I think it would be, great. I mean, one thing that I would say is, I think it's absolutely necessary for you guys as lawyers to know when to see that somebody's trying to pull the wool over your eyes and what questions to ask of an expert witness. But definitely what you want is somebody who really knows the data, because there's a lot of rules. I mean, so we hear that traditional thing from Samuel Clemens about lies, damn lies, and statistics, and that you can make statistics be anything you want. That's true if you're not using the rules that we've set up for statistics. And those rules really aren't known outside of people who, are statisticians. There's a lot of things you can't do. Two-tailed versus one-tailed test. Martina, I know you know all of the BS associated with the one-tailed test, but essentially what a one-tailed test does is it makes you twice as likely to find a significant result as if you use a two-tailed test. Now, no one would know what to look for if they weren't a statistician or a researcher. And there's other things as well. There's other assumptions that you can't violate. Otherwise, your conclusions aren't real. So it's absolutely essential that if your case, something you're trying, is going to hinge on statistical evidence, you want to have an expert who knows exactly what they're doing with the data.
Mm-hmm. Yeah, I guess I'd be very hesitant to introduce that sort of expert just because there's so many of these other rules that, like, how much of that is going to go over the judge's head or the jury's head.
Yeah, I totally agree with that. I mean, some of the reason why we don't talk about them outside of, even when we do talks in science, there's some things that I won't bring up because I'm not sure if the other speech and hearing folks that I'm talking to know enough about stats to know why I've done something. So it's definitely a problem to think about. I think if you have somebody who's a good science communicator who can illustrate why they're different, why they're different and why you need those rules, that might help. But one thing that I would say is, like, if you have something that's clear cut, if it is the same result, one-tailed test, two-tailed test, with these assumptions broken, with these assumptions not broken, definitely introduce it. But if it's something that's going to get cut down in, in the weeds, where it's like only statistics nerds are going to like know what's going on, it might not be worth the trouble. But of course, that's up to you to decide. But
I mean, it seems like a way to manipulate the jury, right?
Yeah, I mean, and hopefully you'd be manipulating them towards the truth. But yeah, you could certainly introduce statistical evidence that's done incorrectly to sway the jury. If anybody is on Twitter and you've looked at any of the like fake science around masks, which I'm not saying that there's definitely some fake stuff around masks, and there's numbers that'll back it up, but of course these numbers are done incorrectly. They're using the science incorrectly, or they're using rates of sickness incorrectly to argue against that masks are something we should be wearing, or distance learning is something we should be doing. The arguments are there, and clearly people are swayed by these arguments and not by the others. So yeah, it's definitely used to manipulate a lot. And the more you know about what you're looking at, the more you can argue against it and show opposing evidence. But Martina, you said, oh yeah, a reason to get a consultant is if the other party is introducing statistical evidence. Yeah, definitely.
All right, unless there are any other questions, I think that's just about time and then some. So thank you so much.
Yeah,